Hi, thanks for joining us today in the week 11 review session. Make sure if you have a question you can type that into the chat window, especially if there are any questions that you would like addressed. All right, this week we talked about triple integrals and changing the order of integration on those integrals. We also looked at applications of integration related to geometry, such as not only finding the area of a region or finding the volume of a solid, but also finding the surface area or the mass of an object. Related to physics, we can also talk about finding moments and the tendency of something to cause turning or inertia, and that's the tendency of an object to stay in its current status. All right, so let's take a look at this problem where we're asked to write an iterated triple integral to find the volume of the solid where both all of x, y, and z are, this should be a z, are greater than or equal to 0 and bounded by the surfaces x plus y equals 2 and z equals 3 minus 3/4 y squared. Okay, so if I take a look at this, the surfaces that were given, I can think of the xy plane, and if I solve for y, this is going to be negative x plus 2, or I could solve for x and have a negative y plus 2. Anyway, we see this line, and I'm only going to draw it in the first quadrant because we know that each of x and y have to be greater than or equal to 0. This has a y-intercept of 2 and an x-intercept of 2. So that's that first region. The second region, well, not the region, but the surface, if I consider the yz plane, z goes between, or I'm sorry, z equals 3 minus 3/4 y squared. That's a parabola that opens down. And so I could see that I've got a z-intercept of 3. If I solve for 0, I'm going to get a y-intercept of 2. And then if I were to solve this curve in terms of y, I'm going to get y equals the square root of 4 minus 4/3 z. Okay. So suppose we're told that we want to write this integral in two different forms. So we want to find the volume of the solid using, first of all, dv to be dz, dy, dx, and then dy equals dx, dy, dz. All right, so let's tackle the first one. Since we're finding the volume of a solid, we know that the volume of a solid we can get by integrating over the three surfaces 1 dv. Okay, so if I want to use dz, dy, dx, and my function is f of x, y, z is 1, we can start with the outermost bounds. Now keep in mind the bounds need to be numbers for the outermost, and these are paired with x's, so these are x bounds. Then we have y bounds, and these are going to be curves, and it curves in terms of x. Yx, well, that's because that's what my outermost bounds are. And then my bounds for z are going to be surfaces. Okay, and those can be in terms of x, y, or both. Okay, so if I take a look at my solid, I want to find the outermost bounds first, dx. Okay, the book works through finding the bounds for the innermost integral first, and that's perfectly fine as well. Okay, so suppose we consider dx. Well, if I look at my three-dimensional surface. Here's x. X goes from 0 to that value right there, or I can also think of it as moving, I can think of a point on that back YZ plane. And if I'm on the YZ plane, then x is equal to 0. And then it moves up and it's going to stop where that line segment is. Well, that line segment is y equals a negative x plus 2. Okay. But I'm thinking of that as being numbers. So if I think about x, x is going to be between 0 and 2. It can't get any bigger than 2. Okay. To find my bounds for y, I like to consider what if I were looking from straight down toward the xy axis or xy plane from the z axis. And so I can think of, well, what's the relationship between x and y? And that's where we have that line, y equals negative x plus 2. So we're told that y is at least as big as 0, and then it goes up to negative x plus 2. So I have y equals 0 to y equals negative x plus 2, or 2 minus x. Okay. And then finally, for the bounds for z, I can think of z as going from this bottom surface up parallel to the z-axis to this curve. And that curve, or that surface is based on the relationship between y and z. And we know that z equals 3 minus 3/4 y squared. So z is going to go from 0 to 3 minus 3/4 y squared. And that's the first way, or one way, that we can write this iterated integral. Okay. A second way we can do this is look at triple integral with dx, dy, dz. Again, so z is the outermost bound, and then y, and then x, working outside in. So z has to be numbers. So z, if I just give possible values for z, z goes from 0 up to the maximum value there. And according to my yz graph, the maximum value that z can be is 3. So this is going to be z goes from 0 to 3. Okay. If I consider y, again, I can consider the yz plane. And that's where I have that parabola. Z equals 3 minus 3/4 y squared. But this time I want to do bounds for y. So the y goes from 0. This is y equals 0. Y goes from 0 to the square root of 4 minus z. So again, if I solve no, that's not right. 4/3 z. So y goes from 0 to the square root of 4 minus 4/3 z. Okay. And then finally we have x. Okay. And if I'm looking at x, so I'm again going from this back YZ plane up to x, and I'm using my graph that I can work with on the XY plane, but this time I want to consider x going from zero up to this line, and so that would be x equals a negative y plus 2. So this would be x going from 0 to a negative y plus 2. And I would be integrating the function 1. Okay, any questions on that? All right, let's take a look at another one. Let's rewrite the iterated integral. The integral from 0 to 2, 0 to 4 minus x squared, integral from 0 to 4 minus y of z times the square root of 4 minus y dz dy dx. Okay? We want to rewrite this as an iterated integral with order of integration dx, dz, dy. And then we want to evaluate the integral. Okay, so let's try to work through this and also draw a sketch of the solid. All right, so working out in, we know that x is bounded between 0 and 2. Y is bounded between 0 and 4 minus x squared. And z is bounded between 0 and 4 minus y. Okay. So if I pair these two bits of information together, I'm going to graph the curve in the xy plane. So we've got a parabola that opens down, has a y-intercept at 4, and an x-intercept at 2, 0. Okay. If I wanted to solve this for x, it'd be x equals the square root of 4 minus y. I'm not taking the negative square root because we know that y is staying above 0. Okay. All right, if I take that bit of information and I try to graph the three-dimensional solid, okay, I can think of that parabola as being positioned there. And that parabola doesn't change as a function of z, so I can think of that parabola extending kind of just, it's not a cylinder, but it would be like a solid that sits between the YZ plane and the XZ plane. And so we can picture that there. And then this last bit of information, that z is less than or equal to 4 minus y. Well, I could graph the extreme, that z equals 4 minus y, and so there would be intercepts on both axes at 4. Okay, and so we'd be looking at this region here. So graphically, what that means is we would have a plane that, I can use blue, a plane that slices the 3D space, and then it extends this way. Okay. And it's going to cross the z-axis at 4. It's going to cross the y-axis here at 4. And so then we can also picture that it's going to slice this solid that we created with y and x. And it's going to slice, so x went up to 2. And so I can think of this surface on the xz plane as a rectangle, a 2x4 rectangle. On the YZ plane, there's going to be a triangular surface. And then this blue plane is going to slice down and is going to cause kind of a parabola shape from this point, which is 2, 0, 4. XYZ is 2, 0, 4, and then it's going to come down like that. So there's our three-dimensional object. There's our surface, I should say. And we want to integrate z times the square root of 4 minus y over that surface. But first we want to change the order of integration to be dx, dz, dy. Okay. Okay, first up is y. The bounds for y is going to be are going to be numbers. So we can see that y goes from 0 to 4. Okay. Next is z. And if I consider the yz plane, which I have, I already have that right here. So I can write z as a function of y because I know I'm still going to integrate with respect to y. So I can think of z going from 0 to 4 minus y. And then for x, I can think of moving from this back plane on the yz plane forward, and it's going to intersect this parabola shape region. So that means x is going to go from 0 to the square root of 4 minus y. And we are integrating z times the square root of 4 minus y. Now, why would we change the bounds for this? This is one where it may not be terribly difficult to integrate initially with respect to either y or z, but looking ahead, if I, for instance, were to integrate with respect to y first, I would end up getting 4 minus y to the 3/2 power, and then I would evaluate that for instance, I would evaluate that, and it might end up being a trigonometric substitution. So it's likely going to be easiest if we integrate with respect to x first. Okay, so let's go ahead and do that. So I'm going from 0 to 4, from 0 to 4 minus y, and then integrating with respect to x. This is going to be z times x times the square root of 4 minus y. Integrating the evaluated from 0, x equals 0 to x equals the square root of 4 minus y. So continuing, this is the integral from 0 to 4. The integral from 0 to 4 minus y. And so this is going to be z times square root of 4 minus y times the square root of 4 minus y. So that's just going to be 4 minus y. And then I'm going to integrate with respect to z and then y. So then this is going to be z squared over 2. 4 minus y will be considered a constant. And I'll evaluate that from 0 to 4 minus y. So this becomes 4 minus y to the 3rd power over 2 dy. Integrating this is going to be negative 4 minus y to the 4th power over 8, evaluated from 0 to 4. So this is going to be 0 minus a negative, plug in 0, this is going to be 4 to the 4th over 8. So this will be a positive 32. Okay, and that's our volume. Oh, that's not a volume. That is the value of that triple integral. All right. So when we talk about the geometric applications of triple integral or integration, we could integrate over a region, and this would give us the area of the region. We could integrate over a three-dimensional surface, and that would give us the volume of the surface. We can integrate over a region of 1 plus the partial derivative of f squared plus the partial derivative of y squared, integrating over the area, and that would give us the surface area. And then one final geometric piece that we can consider is that the mass, and we can consider either a two-dimensional or three-dimensional, is if we have the density of a density function and then integrate over a small piece of the region, or we can do a three-dimensional surface again and have a density function and integrate over the small piece of volume. Okay? All right, so we've got a surface area problem here. Let's suppose we find the area of the surface of the cap that's cut from the paraboloid, z equals 2 minus x squared minus y squared, by the cone z equals the square root of x squared plus y squared. So let's first get an image of what's going on here. So we have a paraboloid, and so I can think of z as being 2 minus x squared plus y squared. So I can think of these as almost circular rings from like the xy plane. And so I've got 2 minus that, so that I'm going to have a paraboloid that looks, that's open down, the bowl is down. Okay. And then I have a cone. Z equals the square root of x squared plus y squared, or I can also think of this as z squared equals x squared plus y squared. But since we only have z equals the positive square root, I'm going to only be working with the portion that's above the xy plane. And so that's going to look like this. Okay, so one of the first things that we have to do is find where these two surfaces intersect. Okay, well, I have an x squared plus y squared here. I also know that z squared equals x squared plus y squared, so I can say that z equals 2 minus z squared, or z squared plus z minus 2 equals 0. That factors as z plus 2 and z minus 1. I know I can eliminate z plus 2 because I'm not going to have an intersection in negative for z being a negative 2. So the intersection occurs when z is equal to 1. Okay, and that makes sense because if z is equal to 1, then x squared plus y squared which is that z squared is 1, and I get z equals 1. Okay, so if I then think about this cap that's on quote top of the paraboloid, and I also think about projecting this circle z x squared plus y squared equals 1 onto the xy plane, here's my region over which to integrate my surface area, or to find my surface area. Okay, so again, I'm working with the paraboloid. Z equals 2 minus x squared minus y squared. So I've got the square root of, if I take the partial derivative of f with respect to x, that's going to be a negative 2x, which gets squared. Take the partial derivative of f with respect to y, that's going to be a negative 2y, that gets squared, and I'm going to integrate over my region. Okay. Now, the fact that x squared plus y squared. Let's go back up to our paraboloid. Okay, x squared plus y squared. The biggest that x squared plus y squared is going to be is 1. Okay, because that's where that intersected, and we could see that these circular rings have a narrower radius as we get closer to z equals 2. Okay, so I can think of this region as having radius going from 0 to 1. And given, again, that we have x squared plus y squared, it might make sense to go ahead and change this to polar coordinates. So this is going to be integrating r going from 0 to 1. Theta goes from 0 to 2 pi. This is going to be the square root of 1 plus 4x squared plus 4y squared, but that's going to be 4r squared. And then dA is r dr d theta. Okay. And then we could integrate that first with respect to r. We could use a u substitution where u is equal to 1 plus 4r squared, and then du is going to be 8r dr. So that means r dr is equal to 1/8 du. So this would become the integral of theta going from 0 to 2 pi of, if r is 0, u becomes 1. If r is 1, u becomes 5. And this is going to be the square root of u times 1/8 du. And then d theta, I can go ahead and separate out those integrals. So it's going to be 2 pi times u to the 3/2 times 2/3 times 1/8, u going from 1 to 5. So this will be pi over 4, pi over 2, pi over 6. Times 5 times the square root of 5 minus 1. And there's the area of our surface. Okay. All right, the next topic was then applications related to physics, applications of integration related to physics. Center of mass is one of those topics. Recall, let me back up a second here. To find a center of mass, we take the moment about the y-axis divided by the mass, and the moment about the x-axis and divided by the mass. That's if we're in a two-dimensional space. And recall that the moment about the y-axis is the integral of x times the density function. And the moment about the x-axis is the integral of y times the density function integrated over the region. Now, why does it seem switched? Why do we have x here but a y here? Okay. Well, we're talking about moments. Moments have to do with a turning effect. Okay, so if I consider, for example, the y-axis, and I want to think about turning as it relates to the y-axis, I have to consider the density of my object, but also the distance of the object from that point of reference, or in this case, the y-axis. So, and then we measure the distance from the y-axis based on x. Okay, so this is where we get the moment about the y-axis is distance times the density. okay? Or distance times mass, I should say, because as soon as we integrate with respect to area, we're getting the mass of the object, okay? Whereas if I'm rotating about the x-axis, I am needing a distance from that x-axis related to a mass, okay? And so that's why we have the setup as we do, and we call this x bar, y bar, because x bar is often used to denote a statistical concept of average, and this is a weighted average. These are weighted averages, weighted values. Okay, so let's find the center of mass for the region of points with 1 less than or equal to x squared plus y squared less than or equal to 4, and y greater than or equal to 0, given a density function where xy, the density of xy is y. Okay, so in other words, where you're at in terms of x has no bearing on how dense that particle is. Okay, so if I graph the region, I'm looking at x squared plus y squared, which is, I can think of the square of a radius. I'm working with y strictly, or I mean greater than or equal to 0, so I'm not going to graph any circles in the bottom 2 quadrants. So this is x going from -1 to 1, and then again, this is like a square of a radius, which is less than or equal to 4, so that means the radius is between 2 and 1. Okay, so I'm considering this region in here. Okay. All right, so we need to find the center of mass. Well, one thing that we should consider is, do we have any symmetry? Okay. Well, symmetry has to do with the density being consistent, depending on or not depending on where x and y is. So if the region certainly looks symmetric with, as far as the y-axis is concerned. So that would be x equals 0. And since density doesn't depend at all on x, I can say that the region is symmetric about x equals 0. So therefore, the line of symmetry, x bar, will lie on that line of symmetry, which is x. So that means x bar has to be 0. Okay. So that eliminates about 1/3 of the work for us. Okay. So now we need to find y bar, which means I need to find the moment about the x-axis divided by the mass. Okay. The moment about the x-axis is the integral over the region of y times the density function. So I've got y times y, integrating over my region. Because my region does seem like it's in radii, expanding from a radius of 1 to 2, let's go ahead and change this to polar form. So this is going to be r goes from 1 to 2. Theta is going to go from 0 to pi because we're staying in quadrants 1 and 2. Y squared, well, y is r sine of theta. Therefore, that gets squared, and then and then dA is r dr d theta. I've got r cubed times sine squared of theta. I can separate, because my bounds for r do not depend on theta at all, I can go ahead and separate the integral. So I've got the integral from 0 to pi of sine squared of theta d theta times the integral from 1 to 2 of r cubed dr. In order to integrate sine squared, I'm going to change this to 1 minus cosine of 2 theta over 2, that half angle formula for sine, times, I'm going to go ahead and integrate r cubed. That's going to be r to the 4th over 4 from 1 to 2. This will be 1/2 theta minus the sine of 2 theta over 4, going from 0 to pi. This will be 16/4 or 4 minus 1/4. So this will be 1/2 pi. Sine of 2 pi is 0. Sine of 0 is 0. So this would be 1/2 pi times 15/4. So 15 pi over 8 is my moment about the x-axis. Okay. To calculate the mass, I'm going to integrate the density function over the region. So that's going to be y dA. And again, I'm going to use polar coordinates. So this will be the integral from 0 to pi, 1 to 2, the integral from 1 to 2 of r sine of theta, r dr d theta. Again, I can separate the two integrals. This is the integral from 0 to pi of sine of theta, d theta, times the integral from 1 to 2 of r squared, dr. So this will be a negative cosine of theta from 0 to pi times r cubed over 3 from 1 to 2. So this will be 8/3 minus 1/3. Cosine of pi is a -1. I get negated. I get +1 minus a -1. So I've got 2 times 7/3 or 14/3 for the mass. So x bar, y bar is 0, and then 15 pi over 8 divided by 14/3, which is 45 pi over 112. And that's approximately 1.26. Okay. Now going back up to my region, I can just do it here, I guess. .26 means that we're about right there. And that makes sense because the density is y, the density of the region is going to be less dense down here, but more dense up here. So even though there's less region, less area up here, it's more dense. And so it makes sense that that center of mass is above y = 1. All right, that last problem that we're going to discuss has to do with moment of inertia. And moment of inertia, inertia again having to do with the tendency of an object to remain in whatever state it's in. Okay, so it's like resistant to change, so to speak. Okay, and the way that we calculate a moment is really a second moment. So if I'm thinking about the moment about the y-axis, I'm going to integrate over the region x squared times the density function. Okay. So in this case, our region is bounded by the x-axis, x equals -1, x equals +1, and y equals x squared. Okay. And so therefore I can say that this is the integral from -1 to 1. Y goes from 0 to x squared of x squared times 7y plus 1. And I'm integrating first with respect to y, then with respect to x. So integrating from -1 to 1 of, this is going to be x squared times 7/2 y squared plus y, evaluated from 0 to x squared. So I'm going to clean that up a bit first. So that's going to be x squared times 7 halves times x to the 4th plus x squared. And further clean up, this is going to be 7 halves x to the 6th plus x to the 4th, which gets integrated to be 7 halves times x to the 7th over 7 plus x to the 5th over 5, evaluated from -1 to 1. So this is going to be 1/2 plus 1/5 minus a -1/2 minus 1/5. So I get 1 plus 2/5 or 7/5 for that inertia about the y-axis. Okay. All right, so that wraps us up for a brief review of the topics for this week. Stay tuned next week for more review as we approach the third and final exam for the semester. Have a great weekend and keep studying hard.